Okay, so AI, it's everywhere, right? I
Yeah.
mean, you can't escape it these days.
You really can't. It's just exploding. And one of the things I always notice is that when a topic gets really popular really fast,
Everyone seems to be speaking this whole new language.
exactly, like overnight, there's a new vocabulary. And if you're not up on it, you feel a bit lost.
Totally. And it's like you want to get a handle on it, you
Yeah.
know? But where do you even start with all this new stuff?
Well, how about we go back to basics, like really foundational stuff, the core
Yeah,
concepts?
strip away all the hype.
Yeah.
Just get a clear understanding of the essentials.
I think that's a great place to start. And actually, there's a really useful resource for exactly that.
Oh, let me guess. Some super dense academic paper filled with jargon.
Not quite, actually. It's a standard published by ISO and IEC,
Hmm.
the International Organization for Standardization, and the International Electrotechnical Commission.
Oh, wow. So it's like a globally agreed upon framework.
Exactly. And it's called ISO IEC 22989.2022. It's all about laying out the foundational concepts and terminology for artificial intelligence.
Now, that sounds like something we could really dig into.
We could, and actually that's exactly what we're going to do today. We're going to do a deep dive into the first few clauses of this standard.
Okay, so like the introductory chapters if this were a textbook.
Precisely, think of us as your instructors guiding you through the material step by step.
Love it. So where do we start?
Well, our focus today is going to be clauses 1 through 4. They really lay the groundwork for everything else.
So this is from the official ISO IEC 22989.2022 publication, right?
Straight from the source. We're going to break down each clause, explain the key terms and concepts, and by the end, you'll have a much clearer understanding of the foundational building blocks of AI.
Awesome. Let's get started. So clause 1 is called scope. What's the main idea here?
So clause 1 is like our introduction. It sets the stage. It tells us what this document is all about and who it's for.
So it's defining the boundaries of what we're going to be learning about.
Exactly. And one of the main goals of clause 1 is to establish a common vocabulary for AI.
Okay, so we're all on the same page with the language we're using.
Right, because AI is such a diverse field with people coming from all sorts of backgrounds, it's really important to make sure we're all speaking the same language.
Makes sense. So this is kind of like a glossary of key terms.
You could think of it that way.
Yeah.
And Clause 1 also emphasizes that this document is meant to be a foundation for developing other more specific standards.
Oh, so this is like the core, the starting point.
Exactly. And it's also designed to help different groups communicate more effectively about AI.
So like researchers, businesses, policymakers, everyone involved in the AI ecosystem.
Exactly, because the better we can communicate, the better we can collaborate and develop AI responsibly.
Okay, that makes sense. Now, something else that struck me in Clause 1 is that it's not just targeted at tech companies or research labs. It explicitly states that it's applicable to all kinds of organizations.
Yes, that's a really important point. They're acknowledging that AI is becoming increasingly relevant to everyone, whether you're in government, nonprofit, commercial businesses, really any sector.
So having a basic understanding of AI is becoming increasingly important across the board.
I think that's a safe bet as AI continues to become more integrated into our world.
Okay, so Clause 1 sets the scope, tells us who should care and why. Let's move on to Clause 2, which is normative references.
All right, so in most standards documents, this is where you'd find a list of other publications that are considered essential reading alongside the current one. Kind of like required textbooks.
Right, because sometimes you need to refer to other documents to fully understand the context.
Exactly. But here's the interesting thing about Clause 2 in this particular standard.
What's that?
There are no normative references at all. It's completely blank.
No other required reading. That's kind of surprising, isn't it?
It is a bit unusual, but I think it actually highlights something important about these foundational concepts. They're designed to stand on their own. They're self-contained.
So you don't need a whole library of other standards to grasp these initial ideas.
Precisely, they've made a conscious decision to present these core concepts in a way that's accessible and doesn't rely on a bunch of external dependencies.
Okay, I can see the logic in that. It's like building a strong foundation before you start adding on all the extra layers.
Exactly. It's back to basics.
All right, so we've covered Clause 1, the scope in Clause 2, normative references. Now let's get to the heart of the matter. Clause 3, terms and definitions.
This is where things start to get really interesting. This is where we build our AI vocabulary.
And this is like the core glossary for the entire document.
You got it. And Clause 3 is pretty extensive. It provides precise definitions for a whole bunch of terms that are used throughout the rest of the standard.
So this is essential reading if you want to really understand what's being talked about in the AI world.
I'd say so. Especially in a field that's evolving as quickly as AI, it's critical to have a shared understanding of the terminology.
Agreed. Now, before we dive into the specific terms, I noticed that they also point us to some online resources in this clause.
Oh, yeah, that's a really helpful addition. For those who want to go even deeper, they direct us to the ISO and IEC online terminology databases.
So if you're a real word nerd, you can keep exploring.
Exactly, and those databases cover a wide range of technical fields, not just AI. So they're a great resource to have in your back pocket.
So for anyone who wants to check those out, the URLs are https://www.isoogo, ejops, https://www.electropedia.org.
Bookmark those now. All right, let's get into the terms themselves. Clause 3 is divided into several subsections, each focusing on a different aspect of AI.
The first one is 3.1 terms related to AI. This seems like the most fundamental starting point.
It's where they define the core concepts that are directly tied to artificial intelligence itself.
All right, so let's start with one that we hear all the time, AI agent. What exactly is that?
So the definition here is pretty straightforward. An AI agent is an automated entity that senses and responds to its environment and takes actions to achieve its goals.
So it's not just passively processing information, it's actively interacting with its surroundings.
Exactly. It has a sense of its environment and it takes actions based on what it perceives.
And it's goal-oriented, is working towards some objective.
Right, which is usually defined by humans who design or program the agent.
Okay, that makes sense. What about AI component? Is that like a piece of a larger AI system?
Yeah, you got it. An AI component is simply a functional element that constructs an AI system.
Okay, so like the building blocks of an AI system.
Right, and those components can be all sorts of things, algorithms, data sets, hardware, software, you name it.
Got it. So we've got AI agents and AI components. Now, what about the big one, artificial intelligence itself? How do they define that?
Well, they actually define it in two ways. First as a discipline and then as a system.
Okay, so there's the field of study and then there's the actual technology.
Exactly. So as a discipline, AI is the research and development of mechanisms and applications of AI systems.
So it's all the scientific and engineering work that goes into creating and understanding AI.
Right. And they emphasize that it's a very interdisciplinary field.
Meaning it draws from a lot of different areas of knowledge?
Exactly, like computer science, mathematics, cognitive science, linguistics, neuroscience, you name it.
So it's not just a narrow technical field.
Oh.
It's very broad.
Very much so. And then the second definition for artificial intelligence is as an AI system.
Okay, so what's the definition of an AI system?
An AI system is an engineered system that generates outputs such as content forecasts, recommendations, or decisions for a given set of human-defined objectives.
So it's a system that takes in information, processes it, and produces some kind of output that's useful to humans.
Right, and those outputs can be all sorts of things, like a recommendation for a product, a prediction about the weather, a diagnosis of a medical condition, anything that helps us achieve our goals.
Okay, so we've got AI agents, AI components, and AI systems.
Yeah.
What if the term automatic or automated that seems to come up a lot in conversations about AI?
So in this context, automatic or automated pertains to a process or system that under specified conditions functions without human intervention.
So it's basically doing its thing without us needing to constantly supervise it.
Exactly like a self-driving car or a factory robot.
Right, but they do specify under specified conditions, meaning there are still limitations to what it can do on its own.
Yes, for sure. It's not like these systems are completely autonomous. They're still operating within predefined parameters set by humans.
Okay, so it's automated within certain boundaries. What about data mining? I hear that term thrown around a lot too.
Right. So data mining is defined as a computational process that extracts patterns by analyzing quantitative data from different perspectives and dimensions, categorizing them, and summarizing potential relationships and impacts.
Okay, so it's like digging through mountains of data to find those hidden gems of insight.
Exactly. And the goal is to find patterns and relationships that we might not be able to see with the naked eye.
So it's using algorithms to help us make sense of large data sets.
Exactly. And they also mention in a note that this definition has been updated from a previous standard, ISO 1-439.2014.
Oh, how so?
They've just made a slight modification to clarify that it applies to the analysis of multiple data sets, not just a single one.
Makes sense. Data usually comes in plural these days.
All right, let's move on to another term, declarative knowledge. What's that all about?
Declarative knowledge is knowledge represented by facts, rules, and theorems.
So it's basically stating what is known without necessarily explaining how to use that knowledge.
Right, so it's like knowing the capital of France is Paris, but not necessarily knowing how to get there.
A perfect analogy, and the standard also points out that declarative knowledge often needs to be translated into procedural knowledge before it can be used to solve problems.
Okay, so there's the what, and then there's the how.
Precisely, and we'll get to the definition of procedural knowledge in a bit.
All right, looking forward to that. Now, what about expert systems? We used to hear a lot about those in the early days of AI.
Yeah, they were kind of the hot topic back then. So an expert system is an AI system that accumulates, combines, and encapsulates knowledge provided by a human expert or experts in a specific domain to infer solutions to problems.
So it's like trying to capture the knowledge and decision-making abilities of a human expert in a computer program.
Exactly, and they were often used in areas like medical diagnosis or financial analysis where you have a lot of specialized knowledge.
Right, so it's like having a virtual consultant.
Yeah, you could think of it that way, although expert systems have their limitations.
Like what?
Well, they're only as good as the knowledge that's been programmed into them, and they can be pretty brittle if they encounter a situation that's outside of their expertise.
Right, so they're not a replacement for human experts, but they can be a useful tool in certain situations.
Agreed. Now, this next group of terms is all about the Internet of Things, or IoT.
Okay, so how does IoT fit into the world of AI?
Well, these days, they're becoming increasingly intertwined. So first, let's define IoT itself.
Okay, so what is the Internet of Things?
According to the standard, it's the infrastructure of interconnected entities, people, systems, and information resources together with services that process and react to information from the physical world and virtual world.
So it's all those devices and sensors that are connected to the internet and collecting data about the world around us.
Exactly like your smart thermostat, your fitness tracker, your car's navigation system, all of those are part of the IoT.
Right, and all those devices generate a massive amount of data.
Huge amounts, and that data is what makes AI so powerful.
Right, because AI algorithms need data to learn and make predictions.
Exactly. So the IoT is kind of like the fuel for the AI engine.
Okay, so what about an IoT device? Is that just any device that's connected to the internet?
It's more specific than that. An IoT device is an entity of an IoT system that interacts and communicates with the physical world through sensing or actuating.
Okay, so it's not just passively connected, it's actually interacting with this environment.
Precisely. So it might have sensors to collect data about the temperature or the light or the motion, or it might have actuators to control things like motors or switches.
Okay, so sensing and actuating are the key actions of an IoT device.
Right. And the standard points out that these definitions are based on and adapted from another standard ISO IEC 2924.2021, which is specifically about the IoT.
Makes sense to build upon existing definitions. And what about an IoT system? Is that just a collection of IoT devices?
An IoT system is a bit more than that. It's defined as a system providing functionalities of IoT.
So it's the whole ecosystem, the devices, the network, the software, the applications that allow everything to communicate and work together.
Exactly. And those functionalities can be all sorts of things like data collection, data analysis, control automation, you name it.
Okay, so we've got IoT, the big picture, then IoT devices, the individual actors, and then IoT systems, the whole interconnected ecosystem.
Exactly. And as AI and IoT continue to converge, we're going to see more and more systems that combine the two.
Like AI-powered smart homes or self-driving cars.
Precisely. All right, let's move on to another really important term, knowledge. What does that mean in the context of AI?
Yeah, because knowledge seems like a very human concept.
It is, and that's why the definition here is really interesting. So knowledge in AI is defined as abstracted information about objects, events, concepts, or rules, their relationships, and properties organized for goal-oriented systematic use.
Okay, so it's not just raw data, it's information that's been structured and organized in a way that's meaningful and useful.
Right, and the notes here are really important. They emphasize that in AI, knowledge doesn't imply any kind of cognitive ability or understanding the way it does for humans.
So it's not like AI systems are conscious or self-aware?
No, not at all. It's simply a way of representing information in a way that AI systems can process and use.
Okay, that's a key distinction.
Right.
And they also mentioned that information can be represented in either numeric or symbolic forms.
Right, so it can be numbers, equations, formulas, or it can be symbols, words, concepts.
Okay, so it's a very broad definition of knowledge that encompasses both quantitative and qualitative information.
Exactly, and the final point they make is that information itself is essentially data that's been given context.
So data is just the raw material, and information is what we get when we process and interpret that data.
Precisely, and that context is what gives the data meaning and makes it useful for AI.
I know that makes a lot of sense. Now, what about the term model? We hear that a lot in discussions about AI and data science.
Yeah, model is a really fundamental concept, so let's break it down. In this context, a model is a physical, mathematical, or otherwise logical representation of a system, entity, phenomenon, process, or data.
So it's a simplified representation of something that captures its essential features and relationships.
Exactly, and they point out that this definition has been updated from a previous standard, ISO IE 18023-1.2006, to specifically include data.
Okay, so now it explicitly recognizes that models can also represent data itself.
Right, which makes sense given how central data is to modern AI.
Absolutely. Now, what about the term narrow AI that seems to come up a lot when people are talking about the limitations of current AI?
Yeah, so narrow AI is defined as a type of AI system that is focused on defined tasks to address a specific problem.
Okay, so it's like an AI that's really good at one thing, but not so good at anything else.
Precisely like a chess-playing AI or a spam filter, they're designed to excel at a particular task.
Right. And the note here contrasts narrow AI with general AI, which would be an AI that has a much wider range of capabilities, more like human intelligence.
Exactly, and general AI is still largely hypothetical. We haven't achieved anything close to that yet.
So for now, we're mostly dealing with specialized AIs that are good at specific things.
Right, although those specialized AIs are getting increasingly sophisticated.
True enough. Now, what about the term prediction that seems to be a key output of many AI systems?
Prediction is the primary output of an AI system when provided with input data or information.
So it's the system's best guess about what's going to happen or what something means.
Right, and the notes here clarify that a prediction can be followed by further actions like recommendations or decisions.
So it's not just the endpoint, it can be part of a larger process.
Exactly. And they also point out that a prediction doesn't necessarily refer to the future. It can also be about the present or the past.
Oh, so like if an AI is analyzing an image and identifying objects, that's also considered a prediction.
Exactly. Or if it's translating a text from one language to another, that's also a prediction.
Okay, so it's a broad term that encompasses any kind of output that's based on the system's analysis of input data.
Precisely. All right, now remember we talked about declarative knowledge earlier.
Yeah, but what?
Well, now we're going to talk about procedural knowledge, the how.
Okay, bring it on.
So procedural knowledge is knowledge which explicitly indicates the steps to be taken in order to solve a problem or to reach a goal.
So it's the instructions, the recipe, the algorithm.
Exactly. It's the how-to knowledge.
And often you need both declarative and procedural knowledge to successfully solve a problem.
Right. You need to know what's true, and you need to know how to use that knowledge.
Makes sense. Now, what about the term robot that conjures up images of science fiction?
It does, but the definition here is a bit more down to earth. The robot is an automation system with actuators that performs intended tasks in the physical world by means of sensing its environment and a software control system.
So it's a physical machine that can interact with the world around it.
Exactly, and it has sensors to perceive its environment and actuators to move and manipulate objects.
And it's all controlled by software.
Right, which is what makes it intelligent, or at least gives it the appearance of intelligence.
Okay, so it's the combination of hardware, software, and sensors that makes a robot a robot.
And the notes here mention that robots are often classified based on their intended use, like industrial robots or service robots.
Right, so there are different types of robots for different jobs.
Exactly. And they also point out that robots rely on various sensors to perceive their state and environment.
So they need to be able to sense things like position, temperature, pressure, light, sound, all the things that we take for granted.
Absolutely. Those sensors are their eyes and ears.
Now, what about robotics? Is that just the study of robots?
Robotics is the science and practice of designing, manufacturing, and applying robots.
Okay, so it's the whole field that encompasses everything from building robots to programming them to figuring out how to use them effectively.
Exactly. It's a multidisciplinary field that draws from areas like mechanical engineering, electrical engineering, computer science, and more.
So it's a pretty broad and challenging field.
Very much so, but also incredibly exciting given the potential of robots to transform our world.
All right, let's move on to semantic computing. What does that mean?
So semantic computing is a field of computing that aims to identify the meanings of computational content and user intentions and to express them in a machine processable form.
Okay, so it's about enabling computers to understand the meaning of data and instructions, not just the syntax.
Exactly. It's about going beyond just processing symbols and trying to grasp the underlying semantics.
So it's like teaching computers to understand the world the way humans do.
In a way, although we're still a long way from that.
Right, but semantic computing is a step in that direction.
Absolutely. It's a key area of research in AI, and it has the potential to revolutionize the way we interact with computers.
Now, what about soft computing? That sounds kind of fuzzy.
Well, it kind of is. So soft computing is a field of computing that is tolerant of and exploits imprecision, uncertainty, and partial truth to make problem solving more tractable and robust.
So it's acknowledging that the real world is messy and unpredictable.
Exactly, and that traditional computing approaches, which often rely on precise rules and perfect data, can struggle in those kinds of environments.
So soft computing is more flexible and adaptable.
Right. It uses techniques like fuzzy logic, probabilistic reasoning, and evolutionary algorithms to deal with uncertainty and ambiguity.
Okay, so it's a different way of thinking about computation, one that embraces the messiness of reality.
Precisely. And it's becoming increasingly important in AI as we try to build systems that can operate in the real world.
Now we have two terms that seem to be contrasting with each other: symbolic AI and subsymbolic AI.
Right, so these represent two different approaches to AI that have been around for a while.
Okay, so what's the difference?
Symbolic AI is AI based on techniques and models that manipulate symbols and structures according to explicitly defined rules to obtain inferences.
So it's about using symbols to represent knowledge and rules to manipulate those symbols.
Exactly. It's kind of like traditional computer programming where you have variables and functions and you define the logic of the program.
Okay, and subsymbolic AI.
Subsymbolic AI is AI based on techniques and models that use an implicit encoding of information that can be derived from experience or raw data.
So it's less about explicit rules and more about learning patterns from data.
Precisely. It's the approach that's used in machine learning and neural networks.
Okay, so symbolic AI is top-down rule-based, and subsymbolic AI is bottom-up data-driven.
That's a good way to put it. And both approaches have their strengths and weaknesses.
Right, depends on the specific problem you're trying to solve.
Exactly. All right, the last term in this section is task. What does that mean in the context of AI?
So a task in AI is defined as an action required to achieve a specific goal.
Okay, so it's the thing that the AI is trying to do.
Exactly, and the notes here clarify that these actions can be either physical or cognitive.
So a physical task might be something like moving a robot arm to pick up an object.
And a cognitive task might be something like classifying an image or translating a text.
Precisely. And they give a bunch of examples of common AI tasks like classification, regression, clustering, dimensionality reduction, and more.
Wow, we really covered a lot of ground there. That was a pretty comprehensive overview of the core AI-related terms.
It was, but there's still more to come. Clause 3 continues with several other subsections, each focusing on a different aspect of AI.
Okay, so let's move on to the next one. 3.2, terms related to data.
All right, so as we know, data is the lifeblood of AI.
Yeah, AI algorithms need data to learn and make predictions.
Exactly. So this section defines some key terms related to the data that's used in AI systems.
Okay, starting with data annotation, what does that mean?
Data annotation is the process of attaching a set of descriptive information to data without any change to that data.
So it's like adding labels or tags to data to make it more meaningful to an AI system.
Exactly. The note here explains that this descriptive information can take the form of metadata labels or anchors.
Okay, so metadata is like data about data, like the data photo was taken or the location where it was taken.
Right, and labels are like categories or tags that we assign to data, like labeling a photo as a cat or a dog.
And anchors are like pointers that highlight specific parts of the data, like drawing a box around a face in a photo.
Precisely, all of these things help AI systems to understand and interpret the data.
Makes sense. What about data quality checking? Why is that important?
Data quality checking is the process in which data is examined for completeness bias and other factors which affect its usefulness for an AI system.
So it's about making sure that the data is accurate, reliable, and unbiased.
Exactly, because if you train an AI system on bad data, you're going to get bad results.
Garbage in, garbage out, as they say.
Exactly. So data quality checking is a crucial step in any AI project.
All right, let's skip ahead a bit to the term input data. That seems pretty straightforward.
It is input data is data for which an AI system calculates a predicted output or inference.
So it's the data that the AI system is given to work with.
Right. It's the raw material that the AI system processes.
And what about production data?
Production data is data acquired during the operation phase of an AI system for which a deployed AI system calculates a predicted output or inference.
Okay, so it's the real-world data that the AI system encounters once it's been deployed and is actively being used.
Exactly. It's the data that the AI system uses to make decisions and take actions in the real world.
All right, so we've covered some key data-related terms. Now let's move on to 3.3, terms related to machine learning.
This is where we get into the heart of how AI systems actually learn from data.
Yeah, this is the exciting part.
It is. So let's start with a term that might sound a bit intimidating, Bayesian network. What's that all about? A Bayesian network is a probabilistic model that uses Bayesian inference for probability computations using a directed acyclic graph.
Okay, I'm going to need you to break that down for me.
Sure, so basically it's a way of representing the relationships between different variables and how those relationships influence the probability of certain events occurring.
So it's like a map of how different factors are connected and how they interact with each other.
Exactly, and it uses Bayesian inference, which is a statistical method for updating our beliefs about the world based on new evidence.
Okay, so it's a way of combining prior knowledge with new data to make more accurate predictions.
Precisely. And the directed acyclic graph part just refers to the way the relationships are visualized. It's like a flowchart where the arrows represent the direction of influence.
Okay, that helps. What about decision trees? Those sound more intuitive.
They do. A decision tree is a model for which inference is encoded as paths from the root to a leaf node in a tree structure.
So it's like a series of yes or no questions that lead you to a conclusion.
Exactly. Each branch in the tree represents a decision based on the value of a certain variable, and the leaves of the tree represent the final outcomes or predictions.
So you start at the root of the tree and follow the branches based on the answers to the questions until you reach a leaf.
Precisely. And decision trees are often used for classification tasks, like deciding whether to approve a loan or not based on the applicant's credit score, income, etc.
Okay, that makes sense. Now, what about the term hyperparameter? I hear that a lot in the context of machine learning.
A hyperparameter is a characteristic of a machine learning algorithm that affects its learning process.
So it's like a setting or a knob that you can adjust to control how the algorithm learns.
Exactly. And the notes give some examples of hyperparameters like the learning rate, the number of hidden layers in a neural network, the regularization parameter, and so on.
And these hyperparameters are set before the actual training of the model begins, right?
Right. They're not learned from the data. They're set by the human who's designing the model.
And finding the right hyperparameters can be tricky, right?
It can be. It's often a process of trial and error, and there's no one-size-fits-all solution.
So it requires some expertise and experimentation.
Absolutely. All right, now let's get to the big one. Machine learning itself. How do they define that?
Machine learning is the process of optimizing model parameters through computational techniques such that the model's behavior reflects the data or experience.
Okay, so it's about using algorithms to adjust the internal settings of a model so that it can accurately predict or classify new data.
Exactly, and those internal settings are called parameters.
Right, and those parameters are what determine how the model behaves, how it makes predictions.
And the optimization process is about finding the best set of parameters that will produce the most accurate results.
Precisely. And that's where the computational techniques come in. They're the algorithms that we use to search for those optimal parameters.
It's a very data-driven process.
It is. It's all about using data to teach the model how to make accurate predictions.
And what about machine learning algorithms? Are those the things that actually do the learning?
Yes. A machine learning algorithm is an algorithm to determine parameters of a machine learning model from data according to given criteria.
Okay, so it's the recipe, the set of instructions that tells the computer how to learn from the data.
Exactly. And the standard gives linear regression as an example.
Oh yeah, that's a classic statistical method for finding a linear relationship between two variables.
Right. So if you have a bunch of data points and you want to find a line that best fits those points, that's linear regression.
And in machine learning, we use algorithms like linear regression to find the parameters of a model that will best fit the data.
Precisely. And there are all sorts of different machine learning algorithms, each with its own strengths and weaknesses.
So choosing the right algorithm for a particular problem is an important part of the process.
It is. It's one of the key decisions that a data scientist has to make.
Okay, now what's a machine learning model? Is that the thing that gets produced by the learning process?
Yes. A machine learning model is a mathematical construct that generates an inference or prediction based on input data or information.
So it's the end result of the training process.
Right. It's the thing that actually makes the predictions or classifications.
And it's based on the data that it was trained on.
Exactly. The data shapes the model.
And these models have internal settings called parameters or model parameters.
Yes. A parameter or model parameter is an internal variable of a model that affects how it computes its outputs.
So they're like the knobs and dials that control how the model behaves.
Exactly. And the values of those parameters are what get adjusted during the training process.
So the algorithm is trying to find the best set of parameter values that will make the model as accurate as possible.
Precisely. It's like fine-tuning the model to get the best performance.
Now, what about retraining? Why would we need to retrain a model?
So retraining is updating a trained model by training with different training data.
Okay, so it's like giving the model a refresher course with new data.
Exactly. And there are a few reasons why you might want to retrain a Model 1 is if the model's performance has started to decline.
So like it's not making as accurate predictions as it used to.
Right. That could be because the data that the model was trained on is no longer representative of the real world.
So the world has changed and the model needs to catch up.
Exactly. Another reason to retrain a model is if you want to adapt it to new patterns in the data.
So if there's new information that the model needs to learn.
Right. And the third reason is to correct for bias.
Ah, yeah, because
Yeah.
if the data that the model was trained on was biased, then the model itself might be biased.
Precisely. And that can lead to unfair or discriminatory outcomes.
So retraining with more diverse and representative data can help to mitigate bias.
Absolutely. All right, let's move on to two terms that describe different approaches to machine learning: supervised machine learning and semi-supervised machine learning.
Okay, so what's the difference?
Supervised machine learning is machine learning that makes only use of labeled data during training.
Okay, so labeled data is data that has been tagged or annotated with the correct answer.
Exactly. So if you're training a model to classify images of cats and dogs, you would need a data set of images that have already been labeled as either cat or dog.
Right, so the model knows what it's supposed to be learning.
Precisely. And semi-supervised machine learning is a bit different. It's machine learning that makes use of both labeled and unlabeled data during training.
So it can learn from both data that has been tagged and data that hasn't.
Exactly. And this can be useful when labeled data is scarce or expensive to obtain.
Okay, so it's a way of making the most of the data that you have.
Right. And it can often lead to better results than supervised learning alone.
Interesting. Now, what about support vector machines? Are those a type of machine learning algorithm?
They are a support vector machine, or SVM is a machine learning algorithm that finds decision boundaries with maximal margins.
Okay, I'm going to need you to break that down for me.
Sure. So imagine you have a bunch of data points that belong to two different classes.
Like the cats and dogs again.
Exactly. And you want to find a line that separates those two classes as cleanly as possible.